it is supposed to be recording.
Yeah, well, it says the recording has started on my end anyway.
Yeah.
Okay. Thank you for attending my first seminar online and in JAX, and we are going to make an introduction to JAX. JAX is a framework that is developing Google, and the point is make a very powerful framework to work with machine learning and other stuff, and probabilistic learning and probabilistic stuff. And JAX the point is to make it that very easily. And in order to do that, JAX is a Python with three main frameworks. One of them is Autograph that make compute automatically, make automatic differentiation and compute automatically gradients or Jacobian or Hessian or whatever. And the other is XLA, and XLA is a framework to compute with GPUs and generic GPUs. And then on top of that is using that is GIT, that is you can take any Python and you say that piece of code is GIT, and then the system made that piece of code compile, and it can compile for your CPU, for your GPU, or for whatever. And that is the point. I am going to use two very good notebooks. They are on internet. One is this, is getting started with JAX, and the other one is this other, a brief introduction to JAX and Laplacian methods.
Screen there. You're not sharing your screen there at the moment.
Oh fuck!
You might want to edit
I
that
have to edit. Oh. Then
No, you should leave that in. You should leave that.
Thank you.
Oh, he's disconnected, has he? Hello, Paco, you've gone.
Bit disconnected.
Yeah, he's clicked the wrong button probably. He's clicked off instead of share or something. That's easily done. I've done that before. It's really annoying. Because it's the big red button. You're inclined to just go straight for it, and it's not that button.
Oh, it's gas. I wonder if it's still recording. We can use all this material.
It probably
Make a B-roll or an outtakes. Oh, it's gas.
Well, at least it froze with a decent look of him. Usually it froze with some screwed up face of yours or something,
It sure did. Oh. It looks very powerful, the JAX framework.
It's fabulous, actually. Yeah, I was looking at it yesterday. It's very good. It's very, very good. I was unaware of it. It's part of TensorFlow, or it's a TensorFlow add-on as well. So it's all got the Google power behind it. So it's probably going to get adopted. Now, well, I say that Google are also inclined to just drop stuff as well at the last minute. Generally speaking, their languages tend to stick. So they're not as bad there as they are with Android stuff.
Yes, yes, and it appears useful at the start, like you were saying. Yeah. It was making me think about the way we teach MATLAB in the course, and very MATLAB now, like really it should just be teaching Python and.
Well, you could actually. Well, you could still teach MATLAB, but do it with a notebook.
Oh yeah, definitely do. Oh yeah, you could do. You could do it with a notebook. Can you
Apparently so. Although I've not tried it myself, but apparently notebooks you can use for pretty much any programming language. So now that said, it depends on the version of MATLAB we have installed. We might have to install a newer version at work or in college or whatever. I'm not sure, but the point is that the nice thing with notebooks is you could write a notebook with things purposefully missing. For example, expand the code here, or write your own bit of code here or something, and then at least they can follow through a tutorial, and then it gets to the bit where they have to do, you can then just mark that bit, which would be nice.
Yes. But is there any what's the point of having MATLAB, you know, or teaching them MATLAB, you know, over Python?
Well, it was really for modeling more than anything, particularly with the mechanical guys. We have to teach them because of CFD and all this sort of stuff that they have to model, and I don't know what else that they model in their, you know, Bernoulli fluid dynamics or whatever it is. Hello again.
Hi.
Hey, Paco, how's it going?
I don't know. He closed my team closed.
That's okay.
I don't know when they
Well,
were saying my.
It's still recording, I think. It's still got a little recording for me. So if you want to start again or carry on or whichever you prefer.
Yes, I'm going to carry on.
Okay.
And let's see what happens.
Yeah. Oh.
Oh, wait.
Again.
Now we know what happens.
I mean, he clicks the share button probably. Yeah, it's not letting him share by the looks of things. That's frustrating, isn't it?
Oops.
I spent yesterday rebuilding my office here so I could have a sit down or a stand up office.
When I share my screen, he threw me away.
Yeah, it freezes you, and you're still frozen at the moment.
Well, I see. I think he's good for me.
Oh, really? Oh, he's still frozen my end.
Paco doesn't move that.
Can you see?
Yes.
Yeah.
Yes.
Can you see my screen?
Yeah, that's it. Yep.
Okay.
Just go on.
Okay. Then thank you very much for coming to my introduction to JAX. I'm going to use these two web pages. A brief introduction to JAX and Laplace method. We are not going to see Laplace methods, just JAX. And this other is getting started with JAX and multi-layer perception, convolutional neural network, and recurrent neural network. This is very good. And JAX is a framework to make mostly machine learning, but can be used for other things because you can make automatic differentiation, you can make compilation using time and vectorization and parallelization. And the main elements of JAX are in this nice drawing. Is one of them is grad that will allow us to compute the automatic differentiation the gradient of any code and with this tool in Python. And the only constraint that has to be the code is that it must be a function that call all other functions, but that function has to be pure. And pure means that you don't use global variable. You all the time are using parameter and your local variable. You can use global variable because then the autograph or the automatic differentiation tool can be became crazy because it has to follow everything. And then in order to avoid that, all the functions have to be pure. That is the name that they give. And having that, you can compute the gradient of everything. On the other hand, you can take your code in Python and compile using time automatically, just telling this function is using time, and it's going to be compiled in the moment to the platform that you tell to JAX. It could be a GPU, or it could be your CPU with the more efficient way of using it. And then there is VMAP, and VMAP take a function that is ready only for your data and make it ready to use it for a lot of data. You know what I mean? You program for one sample, but with VMAP, you can then apply that programming that you have done only for one sample, apply to a lot of samples, but that application is automatic and very efficient. Actually, VMAP what does is just replace a traditional loop passing through all your data. but it does that very efficiently because it takes the data, put in the GPU, and execute everything with one shot. And that's the main 3 ingredients. And the point is that all this is mostly transparent for the user because it's just Python. Here we have these 2 lines are the main line of JAX, and that's the main trick. You see, we are using NumPy, and the name of NumPy is ONP because the actual NumPy we are going to use is JAX.NumPy, and then JAX.NumPy is imported as NP, and then from that on, we are going to use to program in NumPy, that is just arrays, but the version of JAX, and they are going to be ready to put in GPU and to do whatever, and without completely transparent for us. Then we're going to use JAX, that is the function that made the compute the gradient, compilation using tail, and the vectorization. This is the VMAP, what I told you. And then this does 2 things: compute the function and compute the gradient. Is like calling to your function and calling to grad at the same time. But now I'm going to start with the tricks, because this is they have a aim with that they want to achieve a goal, but some goals, but they are not so easy. It's not this is not perfect. The first thing is that we are going to use random, and this random is the random of JAX, and this random has to be used all the time, and we are going to be always aware of our key to generate pseudo-random number. This is done because they want us to be able to repeat the experiment and take the control of the random things. That is because they do it, but they make some things that are not standard NumPy. Okay, and that is what I don't say how to install JAX because it's very easy. Just the JAX for CPU is very easy. Just install it, and that is all. It's just pip install JAX, and that is it works. And then here we have an examples of using the old NumPy and the traditional NumPy. And as we can see, it works fast without anything. It works faster with the JAX NumPy without anything. And here starts the basic concept. And as in this tutorial, they are going to use machine learning and neural network. The function that they are going to work is with ReLU, but you can work with any function. Actually, in this other tutorial, the function that they use is logistic, but you can use any function, whatever function. Actually, in the tutorial, in the official tutorial, they use just a square function. And this is ReLU, is just Python, normal Python, and you take a number and you take compute, return the maximum of 0 and the number. That is all that it does. And then with this function, you pass any function, you pass through this, through JIT, and then you get a version just compiled in native code of your GPU or native code of your CPU or whatever, a version of this function. And from that on, this function is going to be faster. And here they give you a version, and the JIT ReLU, you can see, is very, very fast. A lot faster than the other versions. Okay. Like this. Here we have a function is the same, and with in this, what we have seen here is JIT, but JIT, we are not going to use JIT in this way as a call to a function. We're going to use it as a meta instruction. That is the more usual way. And then this is a function logistic, and the next thing that we're going to use is grad. You take any function, you pass any function to grad, and you get the gradient or the derivative of that function. Okay, it's very easy. And then you can call to the function with a parameter, or you can call to the gradient of that function with a parameter. And it gives you the value. You can compute the gradient of the gradient of the gradient. Okay, and here we see an example. This is f, in our case, this is the sigmoid function, and the gradient is this other function, is the slope. And then it's very easy to compute. And that's it. That's the point. You can compute this gradient and see it, and it is it's computing the gradient. Here we are using the third function of JAX, that is VMAP, and this uses vectorized grad logistic. That what it does is take a function, whatever function it is, and then from now on you can call this function. In this function you can pass not only the number in order to compute the logistic, you can pass an array of number, and it's going to go through all that array and calling the function as if you were programming a loop. But this is done in one shot. This is done smartly and very, very fast. And that's the trick of doing that. This is used mostly to work with batches, you know. And that is all. We take here we take a number, 1,000 number from -10 to 10. Here we have 1,000 number, -10 to 10. And then we pass that 1,000 number to the vectorized set version of logistic, and instead of calling, and that's what it does, is calling to grad logistics for every one of these 1,000 number we have here from -10 to 10. But it does that with one shot. You put on the GPU and then execute in the GPU very fast. That is the point of VMAP. That is going to make this loop very, very fast. And that is the three main points of JAX. Then we have here we can compute the gradient of the gradient. Second order gradient is just the logistic, compute the gradient, and then that function, and compute the gradient of the gradient, the second gradient, and then call to VMAP in order to execute it in a parallelized way. And the same, you can call it, and this is the representation, that is just the slope of this figure. Okay, the slope go up, then stop here, and they go down, and then go up again. And this is just the curvature of the first one. Positive curvature, we are going up, and we are at negative curvature. And that's it. And in order to use JIT compilation, the way to use it is with this decorator. And then you can put that decorator in any function, and then that function is going to be compiled before to be used. Automatically, you don't have to do anything. It's going to be compiled for your native platform, and this is going to be executed very, very fast. Okay. And then here we have a comparison of the computation. See, the logistics function takes 10 microseconds and be executed just in Python, but in JIT logistic, in this machine, my machine is slower. In this machine is, you see, 10 times faster, almost 5 times faster. And with the gradient, the same. You compute in 7 microseconds in the interpreted platform, or with the just JAX without GIT, and with GIT is much faster. And that's
actually way faster. That's 1.76 milliseconds and 86.5 microseconds. That's way faster, right?
Yes,
Yeah.
yes. And it will work fine.
Yeah.
And that is all in this tutorial. I start with the Laplace approximation. If you want, I don't know if you know the Laplace approximation. If you want, we can make another seminar with Laplace. I just learning and understand Laplace very well just with this tutorial because it's very good. And then we'll go back to this tutorial. And in this tutorial, I don't like these tutorials now. No. I'm going to go to this other. Yes. This other tutorial is a tutorial about Bayesian network, but first you start with a normal machine learning, and I'm going to put you in the
Right.
I think this is more didactic. And then we already have an introduction to to JAX. And here we have the import that I told you. NumPy is JAX, and the JIT and the grad and the BNP, the same that everything. And the random in order to generate the random. This is the first thing that you have to do with JAX, generate your key in order to work with the key, the random key, and then you work with the random key. If you need more randomness, you have to call to split. And if you want and generate a new key, you have call to split, and then you get two new keys from this other key, and you can have one of the key be the other, and then you can generate random things. If you don't do that, if you don't do this, you can generate with this key, and all the splits are going to be the same, and then you can control the randomness. And that's very good because if you want to repeat an experiment, you can do that, even though you are using random number, because they are pseudo random number and you have the control of them. And that is a point that people that design JAX wanted to keep. And here we have a traditional machine learning data, D1 and D2. One are the red, the other are the blue. The data is the concatenation of both of the things. And all that we are doing here is just NumPy. But if we are working with the JAX with GPU, this actually is on GPU, but we don't have to worry about. It's completely transparent. These are the label of the data, and then we have the data and the label, the target.
So a quick question.
A
quick question there. Just so if you're executing this in your notebook, as you move along, it is just doing a just-in-time compile of that NP concatenate. Is that what you're saying? It'll do.
No, it's not a just-in-time compile. It's a GPU version because we have a GPU. It's a GPU version of this, and I think this is going to be.
Oh, okay. I see.
Or no, I don't know.
Library. Right. I see.
I think JAX is the JAX I have installed is GPU version, and then it's going to work with GPU in a transparent way.
I see. So there are already pre-compiled library functions that are targeted at CPU or GPU, depending on which you select. And then within your code, you're just telling it, here's the parameters, go use that pre-compiled, very fast concatenate in this case, or whatever the library function is. I see.
I think so. Or maybe this function is going to, I don't know, maybe this function is going to work in GPU when you pass D to a GIT function. You know what I mean?
Yes.
I am not sure. I am not sure about that. Maybe the system just keep track of this data, and when you need it on GPU, it put it on GPU automatically.
Yes, I see.
I don't. That is a weak point. And here, for instance, this function a JIT, and then when you call sigmoid, the data you put here is going to pass. Is going to be on the GPU automatically. And this too, or it's going to be, and this code is going to send to the GPU automatically. You don't have to do anything. And this is 2. The sigmoid, we already saw. This is the traditional loss, the binary cross entropy. That is the traditional loss. This is it's almost the same that the mean square error, but with probability. Is the traditional loss that is used with sigmoid. There is not actually the derivative of this is very easy. It's the same, almost the same that the one of the mean square error, but this doesn't matter. This is the loss, and what happened with the loss? We pass the parameter, we pass the data, we pass the target, and it tells me how well fit the data to the target given the parameter. And that's what it does. Our model or neural network is just this. Multiply the weight by the data, and then we get the linear function, the linear value, and then we apply the linear value to the sigmoid, and we get the activation. And what we do is compare the output of my model, that is this, with the actual target, and it does that in this way. Okay. If the target is 1, then this must be 1, 2, and 0. And if the target is 0, this must be 0. That's the point. And then it add all the values of the output on Y, and that is all. And here we have the regularization that is just trying to minimize this. Is the product of the weight by the weights, and it's just the module of the square module of the weights. And what this try to make is make the weights with values, little values, not with bigger values. But we are not going to use this, and that is all. We take we initialize with random number the weights. Okay, we use 3 numbers because we are working in 2 dimensions. We need 3 numbers, one for the X, the Y, and the bias. Here we have 1s in order to add to the data the bias. That is a trick. In order not to have a B, you don't need the weights and the bias. You can have everything in the weights, and that's it. Typical traditional trick, and that is all. And then we can compute what are the best weights, the best W that we can use to fit this data. And how do we do that? Compute the gradient of the loss. Okay, this is the function. And once we have that, call with the parameter, and that gives us how much do we have to change the weights. And that's what we do. And this is just what every framework, everything does, is the gradient descent algorithm. This was, and that is all. And what are we going to do? Just call to step a number of times. In this case, 20,000 times. We're going to call to the function. We're going to save the evolution of the weights in order to see here how it is evolving the learning. And eventually, at the end of this loop, W are going to be here we call to step. Here we call to step, and in W are the data, the real data, the data that are already fixed. And that is all. And so here is the evolution of the learning. As you can see, this is just a logistic regression application.
Well, what are the 5 lines? So you're passing the FNS, weights, and IDX to this animation, but there are 5 lines being shown on the animation, not 3, or 6 lines.
Because yes, it's in order to show you the slope of the how you see this is the slope of the logistic regression.
No, I understand it's a regression, but why are there 6 lines?
They could be more or less, but what they try to show there is the slope of the logistic, because the logistics could have a lower or.
Yeah, no, I understand that, and it's eventually finding the correct slope between the red and the blue. So I can understand it's a regression, but you're showing 6 lines as opposed to.
Yes, it could be 6, it could be 10.
Oh, okay.
They are evenly spaced.
So it's just plus minus.
Yes, the near the line R, the more confident they have.
Oh, okay.
The prediction, you know what I mean?
Right.
Once you go over the green, you are very, very, very right, very certain on your prediction. And when you are under the purple dot or the dark blue, you are very, very, very sure that it is blue, you know.
I see. Yes.
That is the slope of the, and that is the point. At the beginning, the line are very, very spread, and then they go.
I see.
Yeah. And if you push more, you get the line near, and that is the slope of this.
Yes. Yeah. So if you kept running it, eventually those lines would become one. Yeah, I see. Very good.
That slope can be higher.
Yes. Yeah. Very good.
And that is the point. This is the evolution. They started here and they go randomly until they found or on the opposite. I don't remember now. Until they found the right weight. And here I start to say something more. This is the same, just adding the regulation loss. Now we have the loss, and we have the binary cross entropy and the regularization loss, and that is all. We don't have any problem. You can put in the loss whatever you want. You know what I mean? And it will work the same way. No, there is no problem. And I think that is the main idea. Here it is. What it's doing here is computing different set of weights. And this you see they are computing different sets of weights, and then we are having a family of weights that could solve the problem. Each one of these families has a precision. You know what I mean?
Yes.
One are better and another are worse, and then we can weigh that, and that is the point of the Bayesian learning. The Bayesian learning it doesn't learn just one solution. It learns a lot of solutions that are more accurate or less accurate, with more weight or less weight, and that is the point of that. And then with that, the confidence that you get is this one. And as you can see, there is some adaptation to the data. You see.
Yes.
You are more confident in the area of the green, but the green now is curvy because it tried to go near to the data, you know.
Yeah.
In this other, the confidence was all the time the same. You don't adapt to the data. You just have a line.
Yes.
And that is the point of the Bayesian learning. The Bayesian learning adapts to the data because you have a family of solutions. You don't have one family. You can have infinite. If you do that properly, you can have infinite. Okay, that's the point of Bayesian. I don't going to talk anymore about Bayesian. That way you want to, we can make a tutorial about Bayesian. And now this is an introduction. And this is another example. In this example, we are going to use a multi-layer perceptron. And it's as easy as, do you remember that when we use the loss function? Up here, we use the loss function. And just in the loss function, in the loss function here, we put the model. But this data, this can be put in a function. And that's what you do. This function is forward step. Okay, you know what I mean?
Yep.
This now is in a function, is forward step. And now what they are going to use, the loss is the traditional mean square loss. And that what we are going to use, call the function with the weight and the x, get the result, and compute the loss. In this case, this is not the binary cross entropy. This is the mean square. This is more traditional, and because we are using regression. But now, as we are putting the computation in a new function, we can put in that function whatever we want. You know what I mean?
Yeah.
You can make any computation that you want. You can put everything, whatever. You can put any function, sine, cosine, tangent, log, whatever. You can build any function, and it is going to compute the gradient or whatever. But what we have here is just a two-layer perceptron. It's as easy as that. And then now W has a 2-dimension or 1 dimension. It has W. We're going to split in. Yeah, okay. We're going to split in W1 and in W2.
Yeah.
Okay. It could have 2 dimensions, but this I prefer to use only 1 dimension and take the first end to W1 and the other ends to W2. It's okay. And actually, it takes the bias from this W with this equation. Okay, from n to 2n, that is the bias. Okay, it will work. It doesn't matter. This could be any structural data. You can take the data from whatever you want, and then you can compute the gradient of all that code. This is your code. And then we're going to compute the product of the input with the first weight, and add the bias, and then add the bias. I think this is a mistake because they are adding the bias 2 times. You don't have to. And then you compute the logistic. In this case is the tangent hyperbolic, is more or less the same. You compute, and this is the activation of the first layer. And then you concatenate this output with ones in order to have the dimension of the bias. And then you compute the products here. And you should have the bias, but they don't. Okay. As they have added the ones here, the bias is in W2. This is a trick. Anyway, you can put, the point here is that you can put any code that you want here. You can pass any data structure that you want here. The only point is it has to be a NumPy structure. It can be, the opposite. It has to be any data structure that you want to put. You can pass list, you can pass dictionary, you can pass tuple, and the element of all that, you can nest everything. You can nest a tuple in a nest, in a list, or in a dictionary, whatever. There's no problem. But the root element can be number or can be NumPy. Arise, okay.
So that's the only 2 data types it allows. Then it's NumPy and an integer or a floating point.
Yes, you can use NumPy on float points on integer, and that is the data you are working with. And then you can put all that data in a structured way with list, with tuple and with dictionaries or whatever on the structure. Okay, that's the trick. And the point of the automatic differentiation is that it knows how to travel through all that structure, or through all that dictionary, or through all that list. Okay, that's the trick. The trick is that the automatic differentiation is done on the data structure of Python. Okay, you can nest NumPy data. Okay, the NumPy is just matrices with any dimension that you want, but it's the thing where you are going to make the computation. Okay, I don't know do you understand that? Forget about that. You don't have to worry for the moment. You put any code that here, any computation that you need, compute the loss, compute the loss. You can have regularization too, and it's the same. You call to grad, and it compute the grad of this compute the grad of this, and compute the grad of this, and compute the grad of all this. Okay, that is not an nightmare. Try to compute the grad of this span and this dimension span, all of that thing that they have done. You don't have to worry about that because they're going to compute the grad. And here you have your grads. That's what you want. And then update your weights, and that's all. Okay. And that is the point. Then you call a number of time to weights to the step, and the step is going to go learning, and that is what it does. And this is the traditional. This is just overfitting because it's just interpolation. This is pure interpolation. It's interpolating very, very well, but that is not machine learning. Machine learning don't want to interpolate, want to generalize. In order to avoid that, we are going to use the regularization, and this it is going to try to make the weights and not high values. They're going to push the weight to be a lower value. And that is all. If we do that, the model that we learn is this one. This is more intuitive and more general. It generalizes better. It is not making interpolation. That is the introduction. Okay. And here we are. This is Bayesian version. We are computing a lot of different solutions. One are better, other are worse. And then we have this family of solutions. And then we have one. The red one is the maximum likelihood that we already did, but we have confidence that we have other solutions with less likelihood. Okay, we have a margin of confidence in our solution. We have a family of solutions, and that is the Bayesian approach. And I am going to try to give an introduction, very introduction to machine learning. And in order to work with machine learning, JAX is experimenting with this library, stacks. What does stacks? What stacks does is build a lot of functions that we are going to need in order to use machine learning, batch normalization, convolution, dense flattening, ReLU, or whatever. There is a lot. And on the other hand, they give us optimizer. We can use not only the gradient descent that we are using, but more sophisticated optimizer. And then we can use them. This is a trick to see what are we using. We are using GPU automatically. Then we are all the time with the keys, working with the keys. We take the data. And here this is the tutorial. I think I need to finish the tutorial, but this is the introduction. And then when the view you have from this, you can ask me to make another seminar or whatever you are interested in order to make a more deep introduction. Maybe you can follow this tutorial and learn by yourself, and then we can make another seminar or something more punctual, you know. This case, for instance, this function, what it does is you pass the keys, you pass the sizes that you want in your model, in your multi-layer persistron, and then it starts to build a lot of weights, you see. And then you have to generate new keys, and with that new keys you call to random normal, and you build the weights, and you initialize all the weights. And after you have that, in here in parameters you have an array of weights, you know, given by this. You have an array of, the first input is this dimension, the second dimension, the third dimension, and the dimension. And here we have a list of NumPy arrays. Each one is a weight. Okay, it's a matrix. Okay. And then we are going to use the forward pass. Do you remember the forward pass we have here? Forward step here, they have forward pass. Now we don't have only one dimension, because it was only one array of one dimension. Now we have a list of weights. And then we have a list of weights. We can iterate through that list, getting the weight and the bias, compute the call to the ReLU layer, pass the weight and the bias and the activation, the data, and then get new data and pass everything, and eventually compute the final values with the last parameter and the activation multiplied by the last weight plus the biases, and that is the logic. That is the last output, the linear output. And this ReLU layer is just another function. I have a step on it, but it's just, this is ReLU layer.
Yeah.
All that it does is take the parameter. The parameter has two values. It's a list. We have the first are the weight, the second are the bias. Compute the product with the data, add the bias, and call to ReLU. And that is all. And then you can call to, you compute the loss. You can compute the accuracy if you want. And in update, okay. In update, we are going to do the same that we did in a step. Okay, but in this case, we are going to use an optimizer already built. And then what we do with the optimizer already built, we call the optimizer, we call to Adam. We pass a parameter if we want, and we get these three values. This is the init. We are going to init with the params. This is the state. We are going to follow, and that is, and there is a function that is update. Is this function? This is the function that does the step. You pass the gradient, you pass the states, and then you compute the new states. And that is all. The new state is just the value of the, mostly are the value of the param, the updated value of the param.
So Paco, here then you have the Adam call there. Is Adam another JAX call, or have you had to load in another library for Adam?
Yes, it's in optimizer, and it's in JAX.
Oh, in stacks now. Okay, right. So they're built
JAX.
into stacks. Okay.
It's built in JAX.
I wondered
Actually,
if you had
it's,
to call in an Adam library or not.
I know in here. What is it? It was here.
Yeah, it was in this one, wasn't it? Yeah.
It's in experimental in JAX.
Yes, I see.
This can be done in a number of different things. You can build your own stacks. Actually, there are 3 or 4 different stacks versions of this. And on the other hand, there is Google is releasing a TensorFlow NumPy.
Oh.
And maybe the TensorFlow NumPy is going to put to work what they have learned with JAX. Do you know what I mean?
Yeah.
And then if you use TensorFlow NumPy, it's going to be very similar to JAX, because what they have learned with JAX, they are implementing in TensorFlow NumPy. And very likely JAX is not going to have many future, because it's going to be replaced by TensorFlow NumPy. That is just JAX. It's just JAX. But TensorFlow are more marketing and it's more known.
Sure.
And it could be easy for Google to sell TensorFlow NumPy than JAX. And this is just the same. The philosophy is the same. It's going to be very similar. Actually, I saw an example. It was more or less very simple. But I don't know. Maybe JAX evolve and overcome TensorFlow NumPy. But actually, JAX and TensorFlow are from Google. Both of them, and then are from the same people.
Right.
Let's see. And then you call to Adams, and that's Adam. There is a number of different optimizations here, and that is all. And then you call to update. That is the same that we did here. We call to step. Now it's in name update and more sophisticated. That is the same. And then this is the loop. It's a little more sophisticated, but this is the loop. And then you pass the epoch. You call to update. Pass the param, the data, the label, the state, and you get the new param. And actually the param are inside the up states, and that is all. And then you can compute the accuracy, and you can see the accuracy, and you can see how it learns. It works. And that is the trick. If you want to use, instead of using this model is not from JAX. As you can see, this forward is just forward, a function. If you can use actual model from SAC, you can use convolution or whatever, and this is the other. All that you have to do is you call to SACs, use serial, that is the same that PyTorch, the same that can be used with Keras. You put the layer that you want, and here this is the function. Instead of forward pass, it's component. This is all. You have to initialize all the parameters. This function is specialized in initializing the parameter. Here we have the parameter. Here we have the dimension of the output. They don't want to use it. And that is all. From now on, this is your initialize parameter. You can call to comnet in order to evaluate, to compute the accuracy, to compute the loss, and you can learn the same way. The same. Actually, the function is the same, and it learn with convolution. Okay, and I think this is my introduction. In this now here, it built its own layer from JAX. It built its own function. Group. It built a group function that is, it built the initializer, and the actual function, and that is all. You can make your own function. Actually, there is no group in the JAX because it's very, very experimental. I think this is the end of the tutorial. I think you have a overview of JAX as you like it. It's very easy.
So it's really, you've really shown that. So JAX can do pretty much everything that NumPy can do. So you're building convolution layers here, and activation functions and so on and so forth, and you're essentially building a complete neural network. But instead of using slow NumPy expressions, you're now using the much accelerated JAX functions.
Yes. Yes.
Right.
And you don't have to learn any new framework because it's just NumPy.
No, that's right.
You don't have to learn Python. You don't have to learn learning to use the graph, the VMAP, and the GIT modificator, and some tricks. That is not so easy. You need some tricks, and that is all.
So this acceleration would theoretically greatly speed the training of your network. Well, it'll speed up inference as well, but really the advantage here is the speeding up of your training in the first place.
Yes, but sure that TensorFlow is more optimized for that, because you need to work what TensorFlow tells you, and then it's more specific.
Well, have you seen any comparisons then between training the same network in TensorFlow versus this? I mean, is quicker, slower, or how much? I mean, they're showing you comparisons here, as you're seeing there, of JAX versus no JAX. But
I have here a version of my. I don't know if you remember when I showed you the detector, the full convolution that I showed you.
Yes.
I have a version of full convolution in JAX.
Oh, right.
And it trained very fast. It trained very fast. I didn't see the difference.
I was going to say how much difference. It'd be interesting.
No,
to
it wasn't.
Differences are. Is it a 10x difference, as the previous tutorials were showing, or is it slower? It would be interesting to see the difference.
Yes, and here is the time it takes for each epoch. 3 seconds is epoch.
3 seconds epoch.
Yes, I haven't made the comparison, but I have here the version of my fully connected here in Keras, and I could put maybe it is the time here. 3 milliseconds for sample. We can make the calculations. I don't remember how many. 100. The same, because here we have 3 seconds, 100 sample. It's more or less 3.6 milliseconds, and this is 3 milliseconds. We don't know the decimal here. We don't see the decimal here.
Yeah, well,
but this more or less is similar. It's no. I thought it was to be a big difference, but no, it's not so big, the difference.
Well, you'd want to rerun this on the same day, on the same machine, on the same GPU.
This is running the same GPU, different machine, but it's the same GPU. It's in my machine.
I'd still be inclined to try and run it again on the same day on the same machine just to see.
Yes, but it could be just start to execute here, PPPPP, and we can compare. We can start. Ready? Does it work?
Oh, well, don't worry for now. It was just interesting to see if it was significantly quicker.
Oh, I have a problem now. Okay.
Right. Don't worry.
It's fast. It's similar. It's similar. I don't know. Okay.
Very good.
Any question?
Thanks. That's very good.
I'm going to stop sharing. How do you stop sharing? Stop sharing here. And
yeah.
stop recording.
I presume you press the stop record button.